Welcome students. Myself GB Patel, lecturer in Mechanical Department, VPMP Polytechnic. The subject name is Thermodynamics, subject code 3331902. Today we are going to discuss the reverse Brayton cycle. The objective of this video is to derive the coefficient of performance of the reverse Brayton cycle. So let us derive the COP, coefficient of performance of the reverse Brayton cycle. You can see reverse Brayton cycle on PV and TS diagram. There are four processes. Processes 1 to 2 is a reversible isentropic process and it's a compression process. Reversible isentropic process means adiabatic process and compression means compression work is done on the cycle. Process 2 to 3 is an isobaric process and during this isobaric process heat is rejected and that heat is QK or sometimes it's referred as QR. In our derivation we take QK. 3 to 4 a reversible isentropic process and it's an expansion process. Reversible isentropic process means adiabatic process and expansion process, that is why W expansion is delivered by the system. And 4 to 1 is again isobaric process, pressure constant and some heat is absorbed during this process and that heat is Q0 or sometimes it's referred as QA. Q0 is cooling effect or heat absorbed. QK is heating effect or heat rejected by the cycle. You can see here P2 is equal to P3 because 2 to 3 is isobaric process, constant pressure process. 4 to 1 is again constant pressure process, isobaric process, that is why it's a P1 is equal to P4. There are two heat interaction during this cycle. One is QK, another is Q0. So net heat interaction is equal to QK minus Q0. And there are two work interaction during cycle. One is compression work WC and another is expansion work. So net work is equal to W compression minus W expansion. The cycle is in clockwise, anti-clockwise manners. That is why the reverse Brayton cycle is power absorbing cycle. And for a power absorbing cycle, we have to derive COP. If cycle is in clockwise manners, then cycle must be the power producing cycle, and for power producing cycle we have to derive the air standard efficiency. But here the case is anti-clockwise power absorbing cycle, that is why we have to derive the COP, coefficient of performance. So first, RP is a pressure ratio. What is pressure ratio? Higher pressure to lower pressure of cycle. It's a P2 by P1 or P3 by P4. You can see in the diagram the highest pressure of cycle is P2, which is P3, because P2 is equal to P3, and lowest pressure is P1 or P4 because P1 is equal to P4. So pressure ratio is P2 divided by P1 is equal to P3 divided by P4. Now COP of definition of COP, desire effect divided by W net. So in this cycle there are two effects. Q0 is cooling effect and QK is heating effect. So cooling effect is considered as refrigeration effect and QK heating effect is considered as heat pump effect. So we have to calculate or derive two COP, COP of refrigeration and COP of heat pump. So COP of refrigeration is equal to cooling effect divided by W net. Here cooling effect is Q0 and W net is equal to QK minus Q0. Divide this, divide in numerator and in denominator with Q0. So Q0 divided by Q0 1. Here QK divided by Q0 and Q0 divided by Q0 get cancelled. So here 1. Where is QK? You can see here QK. Yes. It's a during isobaric process, constant pressure process. So it's a CP and CP T2 minus T3. Qk is equal to Cp T2 minus T3. Why it's a Cp T2 dt? Because it's a during isobaric process. And where is Q0? Here. It's again at isobaric process, which is 4 to 1. So Q0 is Cp T1 minus T4. Here Cp T2 minus T3, and here Cp T1 minus T4. So I put the value of Qk and Q0 here. Cp get cancelled. So equation is reduces to 1 divided by this value. T2 minus T3 divided by T1 minus T4 minus 1. Say equation A. Second, COP of heat pump, heating effect divided by W net. Heating effect is Qk. W net is equal to Qk minus Q0. Divide by Qk on numerator and denominator. We can get 1 Qk divided by Qk1. Here Qk divided by Qk1 minus Q0 divided by Qk. Put the value of Q0 and Qk. So I can get Cp of this and Cp of this. Cp get cancelled. So equation become 1 divided by 1 minus in bracket T1 minus T4 divided by T2 minus T3. Equation B. So we have a two equation. Equation A is for COP of refrigeration. Equation B, that is COP of heat pump. Now consider process 1 to 2. See the PV diagram or TS diagram. Process 1 to 2 is a reversible isentropic process, and reversible isentropic process means adiabatic process. And for adiabatic process, this is the pressure temperature relation. Here process is 1 to 2, that is why I write here 1 2. T1 divided by T2 is equal to P1 divided by P2 raised to gamma minus 1 upon gamma. Take the reciprocal on both sides. So T2 divided by T1 is equal to P2 divided by P1 raised to gamma minus 1 upon gamma is equal to Rp raised to gamma minus 1 upon gamma. P2 divided by P1 is Rp. You can see here P2 divided by P1 is equal to Rp. So instead of P2 divided by P1, I can put here Rp. Say equation 1. Similarly, process 3 to 4, again isentropic process or adiabatic process. You can see here 3 to 4 is again reversible isentropic process, means adiabatic process. And for adiabatic process, this is the pressure temperature relation. And here process is 3 to 4, that is why I write here T3 divided by T4 is equal to P3 divided by P4 raised to gamma minus 1 upon gamma. What is P3 divided by P4? Rp, pressure ratio. You can see here P3 divided by P4 is Rp. Say equation 2. See the left hand side, right hand side of equation 2 and equation 1. Both are same. That is why equation 1 is equal to equation 2. That is why T2 divided by T1 is equal to T3 divided by T4 is equal to Rp raised to gamma minus 1 upon gamma. Here. Take this, take reciprocal. So T1 divided by T2 is equal to T4 divided by T3 is equal to 1 upon Rp raised to gamma minus 1 upon gamma. Now exchange T2 and T4. So T1 divided by T4 is equal to T2 divided by T3. Add minus 1 on both sides. It's a mathematical okay. So I can write T1 minus T4 divided by T4 is equal to T3 minus T4 divided by T3. Here it is T1 minus T4 divided by T3 is equal to T2 minus T3 divided by T4. Exchange these two, T1 minus T4 and T3. So I can write T3 divided by T4 is equal to T2 minus T3 divided by T1 minus T4. And what is T3 divided by T4? See here, T3 divided by T4 is equal to Rp raised to gamma minus 1 upon gamma. From here, T3 divided by T4 is equal to Rp raised to gamma minus 1 upon gamma. Say equation 3. Take reciprocal. So T1 minus T4 divided by T2 minus T3 is equal to T4 divided by T3 is equal to 1 upon Rp raised to gamma minus 1 upon gamma. Okay. So T2 minus T3 divided by T1 minus T4, that you can see in the equation 1. See here, put the value of equation 3, this equation. Put the value of equation 3 into equation 1. So in equation 1, you can see this portion T2 minus T3 divided by T1 minus T4. See here, this T2 minus T3 divided by T1 minus T4. So that can be replaced by either T3 divided by T4 or Rp raised to gamma minus 1 upon gamma. So here COP of refrigeration is equal to 1 divided by T3 minus T4 minus 1. Here I replace that value by T3 by T4. This value by this T3 by T4. Okay. So T3 minus T4 divided by T4. So it finally go on the numerator. So T4 divided by T3 minus T4. This is first equation COP of refrigeration. If I put instead of this Rp raised to gamma minus 1 upon gamma here, so it will become 1 upon Rp raised to gamma minus 1 gamma minus 1 upon gamma minus 1. This is my second equation. And instead of T3 divided by T4, I can write T2 divided by T1. From where? See this equation. T3 divided by T4 is equal to T2 divided by T1. Ratio of T3 and T4 is equal to T2 to T1. So I can write T3 by T4 is equal to T2 by T1. So my equation becomes T1 divided by T2 minus T1. This is my third equation. So these three are the equation of COP of refrigeration. This is in the form of T3 and T4. This is in the form of T1 and T2. And this is in the form of pressure ratio and gamma, ratio of specific heat. Okay. Similarly, put the value of equation 4, this value, into equation B. So you can see this portion in the equation B. Where is equation B? Yes, here, this portion. So instead of this portion, you can write either T4 by T3 or 1 upon Rp raised to gamma minus 1 upon gamma. Or instead of T4 by T3, you can write T4 by T3, you can write T1 by T2. So you can get three equation for the heat pump also. So COP of heat pump is equal to T3 divided by T3 minus T4, or heat pump, COP of heat pump 1 upon 1 minus 1 upon Rp raised to gamma minus 1 upon gamma, or this form. Okay, so these three are the equation for COP of heat pump. Okay, these are the final equation. Thank you.